Well, she's still got our movement.
All right, page 17. Okay, so we're going to talk about one-side limits and continuity, and the notation that's going to go into place in terms of showing whether a graph is continuous or not. So I think a lot of this will feel connected with what you've seen before. It's just that we have maybe a more formal way of representing what we did with arrows now with one-sided limit. So one-sided limit describes the function's behavior from either the left or from either the left or the right side of an x value. So let's say we have a piecewise function here, made up of a parabola and a linear. The parabola is only showing to the right of 1, so it's getting cut off to the left of 1. And then the linear graph x plus 3 is only showing to the left of 1 and it's getting cut off. It's not, the rest of the line is not showing. So if we ask, what is the final limit as x approaches 1, using knowledge that you that we learned from our quiz, what would you say the limit would be as we approach 1? Doesn't exist, right? And what you did was you visually saw points on either side and you drew arrows towards your target, and the arrows are obviously not headed towards the same y value, so you're able to conclude that the limit does not exist. So before I just talked about, draw the pick 2 points on either side and follow the arrows, right? Follow the arrows. But we have a more now we have a more formal way of talking about these arrows rather than just saying arrows, and that is with the idea of one-sided limit. So left-handed limit is basically what this left arrow is doing. That's basically the behavior of that left arrow coming from the left side of 1. So when you see that 1 with that negative exponent, that is indicating what this arrow is doing. So I'm choosing a point to the left of 1, and I'm following that path towards 1, and I'm asking, where is that graph headed? Where is that one-sided limit? So if we follow the path of the left-handed limit, where's that arrow headed? Towards a y value of what? 4. So that is a one-sided limit. So we know how to do this. It's just that we just now are going to get accustomed to a more formal way of talking about the arrows. And then the right-handed limits would be what we see here. And the right-hand limit would be approaching 1 with that plus. That plus means that we're starting to the right of 1, and then we're following the path of the graph towards 1. So this arrow here is basically that notation. So if we're approaching 1 from the right, what is that one-sided limit? 1, because it's heading towards a y value of 1. And now we can more formally say that, well, because rather than saying, oh, the arrows are not in agreement, we can now say that the one-sided limits are not in agreement because the 4 and 1 are not equivalent. So we say it this way. Yeah, the limit from the left side of x of 1 is 4, and the limit from the right side of 1 is equal to 1. So then we say that the limit, okay, so let's write it this way. So since limit as x approaches 1 from the left of f of x does not equal to the limit as x approaches 1 from the right of f of x. Therefore, the limit as x approaches 1 of f of x does not exist. So I just want to point out on the quiz, I think most of us, I'm about halfway through grading the quizzes, and they all look pretty good. Very good, actually, a lot of mostly A's. But one issue that I want to keep referring to is that when you write your limit statement, that you don't forget about f of x. A lot of students want to write it without that f of x there, because that's not the way that we say it. We say limit as x approaches 1 is equal to, or limit as x approaches 1 does not exist. But make sure that you include your function notation. Okay, I took at most 1 point off if I saw a student not do that on the quiz, but on the test, I'm going to continue taking points off if you don't write the notation. So I know this is the way that we say it, but we don't want to ever write it this way. So this, if we write it this way, right, this is not a complete statement. Okay, we have to have something there, either an expression or a function name or something. So we can't write it this way. Okay, continuity. So continuity is asking, can we walk along the graph without any interruptions? Can we draw the graph without ever lifting up our pen or pencil? If so, if we can, then the graph is continuous at that point. So basically, if there's a hole, if there's a jump discontinuity, if there's a vertical asymptote, then none of those are continuous functions, right? And like this is not a continuous function. We have to lift up our pencil, start at a different point to continue with the graph. And if we do that, then it's no longer a continuous function. So if we want to prove that a function is continuous, now obviously, if you just look at the graph, that's easy, right? Oh, this is definitely continuous. You don't have to, like, why even have to prove it? So, but we do need to know the language around proving whether a function is continuous. So let's say we only had a piecewise function in front of us, and we didn't have the availability of a graph to look to see if the graph is connected. If we follow these conditions, we can prove whether a function is connected or not, using the concept of order pair and using the concept of limits and seeing if everything is aligned with each other. So this is something we need to memorize for our test, but we'll get plenty of practice so that eventually I think you'll feel comfortable. So the first is, does my point exist? Okay. F of C, is F of C defined? Now, you're never going to have to guess where the point is in question. The problem is always going to tell you explicitly what that C value is, or it'll be very obvious within the piecewise function what that C value is. So for instance, if it was a piecewise function like this, the C value would be what, if you have to guess? What X value are we centered around in this problem? Yeah, so even if it doesn't state it in the problem, you can just look at the restriction and the restriction will tell you what that C value is. It's always going to be talking about referring to centered around that number. Okay, so first off, does the point exist? The second is, does the limit exist? Sometimes we can rely on one statement. Otherwise, if it's a piecewise function, usually if there's a less than, greater than around that C value, that's the indication that we need one-sided limit because we have two different functions coming towards the graph and we need to evaluate them separately. So you can put a note here. If there's less than, greater than in piecewise function, then we need to use one-sided limit. Not every piecewise function has less than, greater than. Sometimes you have doesn't equal to and equal to. If that's the case, then we only need one limit statement. But anytime you see less than, greater than with your piecewise function, that's a good clue, hints that, oh, I need to rely on one-sided limits. So if we use one-sided limits, we can decide, okay, are they in agreement? If they are, then great. Our limit passes, we can keep going. If the limit does not exist, then we have a discontinuity, and we'll talk about that discontinuity in a second. And then if both conditions pass, if the second condition passes, we go to the third condition. So third condition is not any new data. we're just looking back at the first two and asking, is the point living where the limit lives? If they are, then great. All three conditions pass, the function is continuous. But then if the limit doesn't live where the order pair lives, then there's a discontinuity, and we would say the limit does not equal to the function or the function at that point. So the third condition is not any new data. You're just looking back and comparing what you gathered from the first two. So when checking for discontinuity, we want to step through each condition in order. So let me just show you a quick example here. There's a point defined. So let's say this is what the graph looks like. So in this case, the point will be defined. It would pass the first condition. Okay. This limit exists. So let's say the graph looks like this. Okay. Would the limit exist? Would it pass the second condition? Yes, right. If I pick 2 points on either side of the graph, it's headed towards the hole, the same hole is headed towards the same y value. The one side limits are in agreement. It would pass the second condition. The third condition is asking, does the point live where the limit lives? This one would fail. Okay, so then this is what it would look like if it fails that third condition. So we have two types of discontinuity. The first discontinuity is what we call a removable discontinuity or a hole discontinuity. This is where the graph can be made continuous by filling just a single point. If I'm only 1 point away from achieving continuity, then we call that a removable discontinuity. So if you write this down here, a removable discontinuity passes the second condition, but fails the third condition. I'll zoom in on that. Removable discontinuity passes the second condition but fails the third condition. So that means the limit does exist, but it just doesn't have that hole filled in. And if you're asking, well, what about the first condition? Think of the first condition as just information gathering. We're not really using the first condition to determine what type of discontinuity. Now, if a function fails the first condition, we know that it's not continuous because the point doesn't exist. But we don't know what type of discontinuity until we get into the second condition. So we always want to at least get to the second condition if the problem is asking for what type of discontinuity. So the first condition, it's more of an information gathering stage. Page 18. Next, we have what we call a non-removable discontinuity. This is a step discontinuity or jump discontinuity. This discontinuity is where the graph jumps from one connected piece of graph to another. So like the first example that we just did, where we saw the one side limits are not in agreement, that's a jump discontinuity. If there's a vertical asymptote in the way, that's also a jump discontinuity. So in this example here, the limit as x approaches -1 from the right. One side is headed towards 3, the other side is headed towards 1. Therefore, the limit doesn't exist. If the second condition fails, we stop because we already know what type of discontinuity we're dealing with. So if the second condition fails, it's a jump discontinuity, and we say it's a non-removable discontinuity. So let's revisit details. from each of the continuity statements, and then we can practice with piecewise functions and trying to determine if a function is continuous. If it's not continuous, then what type of discontinuity can we categorize our graph? So first condition. If the first condition fails, function is obviously not continuous, but we continue to the second condition because we still don't know what type of category of discontinuity we're dealing with. So no matter what happens with the first condition, we gather it and then we move on to the next condition. Second condition is testing if the limit exists. If the second condition fails, then obviously limit doesn't exist. And then we can stop because we already know what type of discontinuity. It is a non-removable discontinuity at that point, at that C value. Remember, you're only going to test the third condition if the second condition passes. So we don't go to the third condition if the second condition is already failing and we already know what type of issue we're dealing with. Okay, so then let's talk about the third condition. If the second condition passes, then we move to the third condition. If the third condition fails, then we also know what type of discontinuity. We know it's going to be a hole discontinuity because the limit exists, but the hole is not getting filled in. It's not matching with the first condition. Remember, the third condition, we're just going back and checking the first two. We're not creating any new data here. We're just revisiting and asking, do we have an agreement between the first and second? And then if all three condition passes, then we know our graph is continuous at that point. Okay, so let's try example 2 together. Okay. Categorize as removable or non-removable. We know here the point in question is the break that we see in front of us. So we know our C value is at 5. Okay. Just by looking at the graph, you know what type of discontinuity are we dealing with? Yeah, it's a second non-removable. But we're just going to walk through our conditions so we can practice writing them out. So the first condition, does the point exist? We know that the C value in question is that break that we see in front of us, so 5. So we'll say, and this is our f of x function. I'm going to call all these f of x. So f of 5 is equal to what? 1. So the point exists. So okay. It doesn't matter if we pass or fail the first condition. We're still going to keep going. We're going to prove that there's an issue with the second condition. Okay, does a limit exist as we approach 5? No. Okay. So limit doesn't exist, but let's just give it more detail as to why it doesn't exist. So let's show each of the conditions. Let's show each of the one-sided limits here. So we'll say limit as x approaches 5 from the left side of 5. Don't forget, write your f of x. What's the limit as we approach 5 from the left side of 5? 2. Okay, so let's write that down. And then limit as x approaches 5 from the right side of 5. Don't forget, write the f of x. That's equal to 1. Therefore, limit doesn't exist. So we can say limit as x approaches. We don't have to say that this doesn't equal to this. I think this is good enough work or justification to conclude that limit as x approaches 5, the full limit does not exist. We can say that this doesn't equal to that, but I think this is sufficient. This is enough data here. Okay, we have to go to the third condition. No, we already know what type of discontinuity, right? So we can say non-removable discontinuity. Is it discontinuous everywhere? Just where? at 5, so at x equals 5. So we want to make sure that we specify the location, because if we just stop without indicating the x value, then we're saying that it's discontinuous everywhere, or we're implying that it's discontinuous everywhere. But we're just specifying, just one single point that there's an issue here, not the rest of the graph. Okay, let's try part B. Again, the point in question here is at 5. So first condition, f of 5 is what? Undefined, right? There's a hole there. There's no point defined, so it's undefined. Okay. Do we keep going?
Yeah.
Yes. Okay. We know it's not continuous, but at this stage, we're not able to prove what type of discontinuity. We have to at least get to the second condition before we can categorize our discontinuity. Okay, second condition, does limit exist? Okay, so don't forget limit as x approaches 5. Don't forget f of x is equal to 1, right? So this is essentially what we're doing here, picking points on both sides of 5, and they're both headed towards the same hole. They're both headed towards 1, so good. We keep going. Is the third condition going to pass? No, we're just comparing these two, right? Now, I want you to write this a very specific way. I don't want you to say 1 doesn't equal to undefined, therefore, therefore it's removable discontinuity. I want you to include these notations here. So I want you to say f of 5 does not equal to the limits as x approaches 5 of f of x. You don't have to say anything about undefined doesn't equal to 1. This is a strong enough statement to indicate that, therefore, we have a removable discontinuity. Don't forget that you're specifying the location of your discontinuity. Any questions? Try part C. Part C should feel a lot like part B, but I think it's a good chance for us to kind of practice writing out these notations. So try part C. Use B as your model.
That it equals infinity or doesn't.
Yeah, you can say does not exist in parentheses infinity. And then we can stop, right? We know what type of discontinuity. Okay, part D. Find the point of discontinuity for the function. Anytime we're talking about discontinuity, we can just zero in on the denominator. We know the denominator, whatever causes the denominator to be zero is going to be an issue. But it's asking, is it removable? So let's just go through our conditions and see what we get. Okay, so first condition, we know our x value is at 3, our c value is at 3. That's going to be the point that we're zeroing it in on. So let's find f of 3. If I plug 3 into the function, is it defined? Yeah, we get 0 over 0, which we know is a whole, but it's undefined, right? The point doesn't exist, so no, it's undefined. Second limit as x approaches 3. So now this should feel like a quiz like question, right? We go through our process. What's the first thing we do? Plug in, right? What do we get? 0 over 0, right? So now we know, okay, there's a hole, and now we can go through our algebraic steps. X squared minus 9 becomes
X minus.
we're expecting a hole, and we see there's a hole, cancels out. Therefore,
X plus 3.
what's our limit?
Or 6.
Fixed, yeah. So direct substitution is our final step. 3 plus 3 is 6. So second condition passes. So we keep going, right? We haven't failed our condition yet. I mean, the first one failed, but remember, we're determining what type of discontinuity. We have to keep going if we can get that second condition to pass. Okay.
How did we get that?
I'm sorry?
I wouldn't have C equals 3 again.
Because it's asking for discontinuity. And if we're looking for discontinuity in our function, we always focus in on the denominator.
We want.
Yeah. So this one, we do have to find it, but we always know where to find it. It's always going to be in the denominator. Okay, third condition. Is the third condition going to pass? No. And how do we write it in a way where we can show that it doesn't pass? Good. Good. So we don't want to say undefined doesn't equal to 6. That's not a strong enough statement. We want to involve these. So this is what I would say. F of 3 does not equal to the limit as x approaches 3. If you want to write out this expression, you can, or we can just call it what? Yeah. So it's up. So I think this is easier, but if you write it the full expression, that's fine as well. But this is all you need to show that you don't have to say anything about the undefined doesn't equal to 6. Just show that these are not equal. Therefore, what type of discontinuity? We have a removable, and specify what? Where? At x equals 6. Now, there's one more part to this problem. It says, if so, okay, and we show that it's a removable discontinuity, what would we need to set f of x equal to so that the function is continuous? So basically, if we can go back and change something, what will we change to allow for that hole to be filled in? This is what I would change here. What can we change? Make f of 3 what? 6, yeah. So basically, there's a hole. If we want to make the function continuous, we can just fill that hole with the point. So we can say to make f of x continuous, let f of 3 equal 6. All right. The graph looks something like this right now. So right, the graph looks something like this right now. There's a hole, the limit exists. But If we want to fill in that hole, we can just redefine f of 3 equal to 6 to allow for the graph to become continuous. Yeah.
Why is there a removable discontinuity at x equals 6 and not x equals 3?
My bad. It is x equals 3. I was looking at the y value. Thanks. My bad. X equals 3. The 6 is the y value. All right, page 19. I'll just do, your homework is up to page 22. So I just want to just show you kind of one example from each problem so that you can kind of have a model to follow as you, you also have the key on the website, but I just want to show you one from each page so that you have something to look at when you're trying the other problems. So page 19. So determine if the function is continuous at C, and then if not continuous, state which condition that the definition of continuity is not satisfied, and then if not continuous or if discontinuous, state whether it is removable or non-removable, and if it is removable, just like the previous problem, what can we redefine the point to allow for the function to be all of a sudden continuous? So let's do 13. And the graph is in front of us, so we already know what we're working towards. Okay, C equals -3. So -3 is here. Okay. Just by looking at this, what type of discontinuity are you expecting here? At -3. Yeah. So we just have to write out the conditions to eventually work towards that end result that we're expecting. So we can say f of -3 is equal to first condition. What's f of -3? 1. Okay, so second condition, limit as x approaches -3 of f of x. Don't forget, right? F of x. What's the limit as we approach -3 from both sides? -2. Okay, so we keep going. We haven't failed yet. Is the third condition going to fail? Yes. So let's practice writing out. Don't say 1 doesn't equal to -2. Write that this notation doesn't equal to that notation. Therefore, what can we conclude? Removable discontinuity. And that's basically part C here. We're just combining all these together into an answer here. I'm not really separating A, B, C, and D. I'm just indicating here. And then if it's removable, we can redefine our f of C, right? Our f of -3. So function made continuous if f of -3 equals what? Yeah, so we're just redefining it, if possible. If it is non-removable, then we don't have to do part C and D. We can just stop and say limit doesn't exist, non-removable discontinuity. Okay, so you'll try a similar process for 5, 15, and 17. I just want to do one from each page here. Okay, page 20. So now we're given a piecewise function. And this one, we don't have the graph in front of us, so we really have to rely on our limit notation and our continuity statement, and then we can kind of walk through. It's more abstract, but we can just rely on our limit statements and go through our process. So what's our C value? 1. Even if they don't say S equals 1, this should be enough for you to know on the test or quiz. You know, this is pretty obvious that the C value is going to be right at 1. Okay. So f of 1 is equal to 4. Second condition, does the limit exist? What do we need to do before we can find the full limit? There's a sub step here. Yeah, we got to look at each side. Yep. And the reason that you know that is if you see less than and greater than on either side of your target, that's an indication that we got to do one side limit because we have two differently defined functions on both sides of 1. We got to do a one-sided limit for each of the separate functions. So we'll do one at a time. Limit as x approaches 1 from the left side of 1. I'm actually going to write out my expression because it'll make it easy for me to do direct substitution. So plug 1 in, we get 2. And then separately, let's look at from the other side, approaching 1 from the right side of 1. Put down the expression that you're going to be working on. Direct substitution, we get 2 as well. Therefore, what can we conclude? Limit. Yeah, you don't have to say, oh, this is equal to this. You can just jump directly to your resulting conclusion, which is the full limit of f of x. Again, some students, they want to feel like they have to write both these expressions. But just call it f of x. That's referring to this entire function. It's equal to 2. Does it pass? Yes. So we keep going, right? We don't stop. Third condition. What do you do with the third condition?
One does not equal.
Does not equal, right? So therefore, we know what type of discontinuity. We don't have to redefine the point. We just have to state what if it's show that it's not continuous or continuous. And then I also want you to categorize what type of discontinuity. So again, don't say 2 doesn't equal to 4. You want to write it out this way. F of 1 does not equal to the limit as x approaches 1 of f of x. Therefore, removable discontinuity at x equals . Uh, 21. Let's try 45. Bottom of page 21. Determine whether function is continuous. Determine support using your continuity statements. So this is x minus 9 over root x minus 3. It doesn't specify what the C value is, but where can we look for discontinuity? Yeah, basically you set the denominator equal to 0 and look for your C value. Yep, so root x minus 3 is equal to 0. Root x equals 3, square both sides, x equals 9. So even though it doesn't specify, we know our discontinuity is at 9. So now we're just going to step through our conditions and prove whether it's removable or non-removable. Okay, so first condition. So we know our C value is at 9. Okay. First things first, what do you do? First condition. F of 9, right? What's f of 9? Yeah, does not exist, undefined. We don't have a point. So we keep going though, right? We haven't established what type of discontinuity, even though we know it's not continuous. Second statement is what? Limit as x approaches 9. Okay, write out your expression. And now just treat this like a quiz problem. First step, direct substitution, we get 0 over 0. What's our strategy for this type of problem? Multiply by the conjugate, good. So top and bottom gets multiplied by what? Good. All right, so try it. See if you can remember your process here. All right, what cancels out? Reevaluate. 6. We haven't failed yet, right? Third condition. How about third condition? Pass or fail?
Fail.
Fails. Okay, so there's a certain way that I want us to write it. Don't say 6 doesn't equal to undefined. Say something about f of 9 and the limit. You can write the expression out, or you can just call it f of x. And this is enough for you to subcategorize, right? We know we are dealing with a removable discontinuity. Okay, I want to do one more problem here. Want to maybe tackle the most challenging ones so that in class, and then have you guys try the rest. So number 4 on page 22, last one we'll do today. So number 4, I know it looks intimidating. You got that k value that's sitting there, but I want to show you what we can do with continuity conditions. So we can use continuity condition to show whether a function is continuous or not. We can also use continuity condition as a problem solving tool if it's asking for, what value is it going to allow for function to be continuous. So I would say, don't get stressed about this. You're just simply going to walk through your continuity condition blindly, and then eventually you're going to come across your answer without even trying for it. You're just going to walk through your continuity condition, and your answer will just naturally appear in time. Okay, so let's go through our conditions here. Okay, so first condition. Well, first off, what's our C value?
10.
Okay, are we good here? Page 22?
Yeah.
Okay, all right, so our C value is 10. All right, so f of 10 equals what? Sorry. F of 10 equals what? Not undefined is what? K, which is unknown, okay? It's unknown. We still don't know what that value is, but we're just gathering information right now, right? Okay.
If you plug in the 10 in the top one, don't you get 0?
It says if x, right?
Well, that's when x doesn't equal to 0, right? But when x equals 10, sorry, for x doesn't equal to 10, but when x equals 10, we need to rely on the second one. Okay, second condition is what? Does the limit exist? Now, I talked about how we would have to do one-sided limit if we see less than greater than. But here, if it says x doesn't equal to 10, that means everywhere except 10. That means to the left of 10 is looking at the first graph. To the right of 10 is also looking at the first graph. So there's no need to do one-sided limit because the limit statement is going to just, it's the same function on both sides. So if you see doesn't equal to, all you need is one limit statement. But just know that you're not going to touch the second statement because this is just a singular point. If you see this, that means this is where the graph is. This is where your connected graph is. And for limit, we only care about looking at the connected graph. We don't care about the island, the potential island from that point. So then we're going to do limit as x approaches 10. And I know this is messy here, but this is just going to be a conjugate method problem here. This is going to work out for us because if I were to plug in 10, I'm going to end up with 0 over 0. And then I can go through my conjugate method, right? So multiply the top and bottom by the conjugate. Things will clean up. Your holes will remove itself. And then you're eventually going to arrive at an answer that gives you 1 over 10. I'm skipping ahead a little bit. Just want to kind of show you what our end result is. So you're going to do this whole conjugate process on your own as you practice. But let's just say we're able to get to our limit is 1/10. Okay, so passes the second condition. What needs to happen if we want the third condition to pass? Yeah, K must be equal to 1/10, right? If I want everything to pass, I have to set this equal to that. So you're able to get to your answer without even trying for it because you're just following through your continuity condition. But for homework, as part of homework, I do want you to work all of this out. I'm just skipping to the end to show you how to solve the problem, but we still want to practice through all these steps. Okay, good. So I think that's able to kind of go through the more involved problems and then leave you the rest to do for homework. So your homework is up to page 22. And then we'll continue with discontinuity. And then if we can get ahead, that's great. I think we can probably get done with all of our new content by Thursday. And that'll just buy us an extra day of review. Our test is next Wednesday. Guys, if you haven't signed up for AP Classroom, if you can do that today, I'm trying to get everyone signed up by this weekend. So I may be reaching out to you individually just to kind of make sure that you can get that signed up. Thanks, guys. Have a great day.
Thank you.
Thank you.
Oh,
There you go.
thank you.
Thank you. See.
Like,
Yeah.
See you guys.
All right, say sugar bomb. Let's go and get it.
Yeah.
Or
yeah.
not like on